Chemical vapor deposition (CVD) is a material production technique that involves depositing a thin coating on a substrate via chemical processes. The method is frequently employed in the electronics, energy, and aerospace sectors. This section will go through the CVD process and its applications. Chemical vapor deposition (CVD) is a process for depositing thin films of materials on a substrate using a chemical reaction between vapor phase precursor molecules and a substrate surface. The basic steps in the CVD process are as follows: substrate preparation, precursor delivery, adsorption and reaction, growth and deposition, and lastly, termination and post-treatment. Substrate preparation: the substrate is cleaned and prepared to ensure good adhesion and uniform deposition of the film. This may involve chemical cleaning, mechanical polishing, and/or etching. Precursor delivery: the precursor molecules are delivered to the deposition chamber as a gas or vapor. Adsorption and reaction: the precursor molecules adsorb onto the substrate surface and react to form a solid film. The reaction is typically initiated by heating the substrate to a temperature where the precursor molecules decompose, forming reactive species that react with the substrate to form the desired film. CVD is carried out at, or slightly below atmospheric pressure with flow rates in the laminar regime. As the gas flows over the substrate, shear forces slow the gas down, resulting in a velocity gradient. Ultimately, the gas velocity drops to zero at the substrate and a boundary layer is formed. Growth and deposition: the reactive species continue to react with the substrate to form a solid film. The film grows layer by layer, with the thickness controlled by the time and precursor flow rate. Termination and post-treatment: the deposition process is terminated by stopping the precursor flow and cooling down the substrate. The film may then be post-treated to modify its properties, such as annealing, etching, or doping. Today, CVD is a basic tool of manufacturing, used in everything from sunglasses to potato chip bags, and is fundamental to the production of much of today's electronics. It is also a technique subject to constant refining and expansion, pushing materials research in new directions, such as the production of large-scale sheets of graphene, or the development of solar cells that could be printed onto a sheet of paper or plastic. CVD is commonly used to deposit conformal films and augment substrate surfaces in ways that more traditional surface modification techniques are not capable of. CVD is extremely useful in the process of atomic layer deposition at depositing extremely thin layers of material. This process requires extremely high temperatures. While this necessitates a substantial heat source, the more significant disadvantage is that some substrates cannot withstand heat upwards of 900 degrees Celsius. One advantage of the CVD process is that because the chemical reactants are gases, it is able to take advantage of the physical characteristics of how gases flow over the substrate surface to build uniform, highly conformal films on irregularly shaped surfaces. CVD is employed to produce a wide range of thin film coatings with desired properties. Thick films can provide enhanced protection against corrosion, wear, and environmental degradation. They are used in applications where durability and resistance to harsh conditions are required. CNTs can be grown on suitable substrates by controlling the growth parameters, such as temperature and gas composition. Hello everyone! Today, I want to share with you my unique journey as a ceramic engineering student. While many may think that graduating is the ultimate goal, I've come to realize that the path we take is just as important as the destination. So, let's dive into my experiences, challenges, and the valuable lessons I've learned along the way. As a ceramic engineering student, I soon realized that this journey provided me with an opportunity for self-discovery. Exploring the diverse aspects of ceramic engineering, I began to unearth my true passion for this field. Every lecture, lab experiment, and project fueled my curiosity and ignited a deep desire to learn more. embracing the learning process wholeheartedly and immersing myself in the intricate world of ceramics. From understanding the behavior of different materials to comprehending the science behind their unique properties, I discovered the beauty of constant growth and learning. While my focus wasn't solely on earning a degree, I enthusiastically engaged in various extracurricular activities. Being an active member of the College of Engineering Women's Volleyball team and taking part in playing the society's game events helped me to lessen my stress and doubts from the course and inspired me to move forward and to have a positive outlook to keep pursuing the course. Internships were an integral part of my education. Recognizing the importance of industry exposure, I sought internships in manufacturing companies such as Tekla. I got hands-on experience in a real production environment, witnessing the entire process from raw materials to the final product. It truly solidified my understanding of ceramic engineering and its practical applications. These internships served as a bridge between theory and practice, preparing me for a future career in the industry. These valuable experiences provided me with an insight into real-world applications of ceramic engineering. As I reflect upon my journey as a ceramic engineering student, I realize that it has been a transformative experience. The journey itself has molded me into a resilient and passionate individual. I've come to appreciate that success is not solely defined by a degree but by the enthusiasm, perseverance, and love for learning that we bring to our chosen field. It is the journey that shapes us and prepares us for the extraordinary path that lies ahead. So, let us continue to celebrate the beauty of the process, for it is in these experiences that we truly find ourselves.